Hello, we have a goal, that is, compositional specification in rewriting logic and in the language mod. We want to show its feasibility and its convenience. We are developing a framework to allow for it. In this video in particular, we show how useful parameterized programming is to that goal. This is a recording of a talk I first gave at WRLA, the Workshop on Rewriting Logic and Applications, held in Thessaloniki in Greece in April 2018. And yes, I will begin with the introduction, oddly enough. Suppose we have two systems, like two trains that go round circular railways, with three stations in a case and two in the other. We have modeled the two systems. We have written specifications for them, and they work nicely in isolation, but they happen to share some parts of the railways. I have drawn them disjoint, but they are really not. So when they are run simultaneously, some kind of control is needed. We use an external controller, like this very simple one, with a single state and two transitions looping on it. The point here is that within this system, mutual exclusion is built in. A transition or the other can be executed at any given time, or known, but certainly not both at the same time. The idea now is to sync the execution of the left transition with the critical section of the first train, that is with it passing through the shared parts, and the same for the right transition and train 2. Thus, when all three systems are run simultaneously and synced, mutual exclusion in the access to the shared parts is guaranteed. This simultaneous execution is represented by this instruction. It specifies that the three systems must be composed and synced according to the two conditions or criteria given. That train 1 is in the shared parts when the controller grants access to it, and similarly for the second train. The criteria make reference to the properties each in shared part, grants 1 and grants 2, that the systems have to define. Again, this is our goal, to be able to compose independent systems, or rather the other way around, to be able to model a complex system by first decomposing it into simpler components, to be specified individually and then assembled together. We have defined the operation of synchronous composition for the right systems in a previous paper. This talk is about the use of parameterized programming in this context to help improve modularity, to encapsulate components, and define interfaces. I will review our previous work in this video, but the focus here is in the use of parameterized programming, as it exists in mod. A quick reminder on parameterized programming is in order. This is a module implementing sorted lists. It is parametric on the sort of the elements in the list. The parameter can be instantiated, for example, with a specification of the natural numbers. Not any module can be accepted to instantiate the parameter. The requirements for a module to be accepted to instantiate a parameter are included in a theory. I have called this one STO set for strict total order. It contains two requirements, the existence of a sort for the elements and the existence of a less than relation defined on those elements. The natural numbers satisfy these requirements. They define a sort, nat, and a less than relation. A view is the means by which we assert that a module satisfies the requirements of a theory. I've called this view nat. It contains mappings of names. It says that the sort that the theory requires with the name ELT is the one that is called nat in the implementation, and the less than relation that it is called the same in this case. In the body of the parameterized module, we can use the sort ELT from the theory qualified with the name S that I have chosen for the formal parameter, and also the less than relation from the theory as well. Finally, we can instantiate the parameterized module. We use the view for that, not the module, because it is the view that specifies in which way the module satisfies the requirements of the theory. These are the same 5 elements of parameterized programming in a diagram. The theory, its module instance, the view, the parameterized module that uses the name of the theory in its parameter list, and the instantiation with the view. This is a typical way to use parameterized programming, where the parameters are static algebraic structures. Our modules, however, are system modules, representing dynamic, evolving systems. For the trains example, the diagram looks like this. The theory controller specifies the requirements to be met by any module that wants to be considered as such. The same for the theory process. The system mutex is an implementation of controller, and the two trains are processes. The parameterized module, safe processes, takes three parameters, two processes and a controller, and the instantiation uses the three views. I will go into each of these components next. We have made three important choices toward our definition of the synchronous composition operation. One is the use of parameterized programming I'm talking about in this talk. Another is the use of properties about which I am talking next. The other is egalitarianism. This means that we treat states and transitions at the same level as first-class citizens. When syncing to systems, sometimes it is natural to use states. That is, that a system has to visit some state at the same time that the other system visits some other. But sometimes it is more natural to sync actions or transitions. Even syncing states with transitions is useful at times. And for such synchronizations to be flexible, it is not enough that transitions are identified by atomic labels, as is the case in some formalisms. We want transitions to be given as algebraic terms, the same as states are in rewriting logic. For example, this is a possible implementation of the first train system. I'm showing the previous diagram up here for easy reference. Two sorts, state and trans, are declared for states and transitions. There is a constructor for each sort, each taking a natural number in this case. The rule label is a term of sort trans that even includes a variable. This is the main difference between an egalitarian module, as we call them, and a standard one, rule labels. The keyword AE mod, by the way, stands for atomic egalitarian module, and it is a keyword we have invented. In the same way, this is a possible implementation of the mutex controller system with two rules, again with labels of sort trans, ground terms in this case. I want to add a remark before going on. We bear in mind the importance of transitions from the beginning of the modeling or specifying tasks. I mean, it is not the case that we model a system in a state-only frame of mind, and then, afterwards, decide that it may be interesting to use the resulting transitions for syncing or whatever. That would make the system more complex and its analysis more expensive, but modeling with transitions allows us to obtain specifications as simple as this mutex one, with just one state and two transitions. This is another reason why we care about being egalitarian. Properties are in other contexts called attributes, ports, observables, and probably other names. They take values at states and at transitions. They constitute the interfaces for systems. Theories, in our use of them, contain the declarations of properties. This is a possible specification of the theory process. It contains a unique requirement, the existence of a Boolean property to inform on whether the system is in its critical session or not. In the same way, a controller needs to define a property grants for each process it wants to control. That is, a property for each appropriate value of its parameter. We see these theories as specifying interfaces for the system. We build properties with this parameterized module PPTY. It takes as parameter a trif. The trif is really a trivial one, only requiring the existence of a sort. When we instantiate the parameter with bool, as in our example, the module declares the sort of Boolean properties, PPTY bool. It also declares the sort stage, that is a term used to refer to either states or transitions. Finally, it declares an evaluation operator at that we use later. It takes a property and a state or transition and produces a value of sort bool in our case. If we want the module train 1 to really be an instance of the theory process, it has to define the required Boolean property. We do so by extending the module train 1. In this way, we keep separated the specification of the internal workings of the system from the definition of its properties. We declare and define the property isInsert part. Its value is defined to be true at the transition moving 1, representing the train moving from station 1 to station 2, and at the state at station 2. It is false everywhere else. Note how properties are defined both at states and at transitions. Finally, you can write the view, stating that the property required by the theory is the one we have just defined in the module. Very similar is the extension of the module mutex. It defines the property grants n to be true while the nth transition is being executed, false otherwise. Thus, the controller grants access to a process by setting to true the value of the corresponding property, so to speak. Finally, we can write the parameterized module that takes two processes and a controller as parameters and instructs on how to synchronize and compose them. This is not an AE mod, but an E mod. That is, it is egalitarian but not atomic. The syncing criteria are as at the beginning, but now referring to the parameters. We could now instantiate with the views for the train and the mutex controller to get a safe trains system. As I said at the beginning, all I have explained up to now has already been theoretically developed. However, its implementation is work in progress right now. Before finishing, I want to say a word about a possible future work concerning the use of assumptions and guarantees to enrich our theories with semantic requirements. Back to the strict total order example. It is not enough that a module defines a less than relation to be considered as strict total order. It must also satisfy some semantic conditions. In mod, it is possible to enrich a theory with non-executable equations, specifying those semantic requirements, like those three for our example. While equations are appropriate for static algebraic data structures, for evolving systems, temporal formulas are better suited. We can, for example, add as a requirement to the controller theory an LTL formula for mutual exclusion. The keyword GRT stands for guarantee. In some cases, also assumptions can be appropriate, and also in the form of a temporal formula. In addition, this could open the door to compositional verification of composed systems using the assume guarantee paradigm. But this is all future work. Up to now, and this is my final summary, we have shown that compositional specification is feasible and convenient in rewriting logic. In this talk in particular, we have shown that parameterized programming is a great tool to improve the modularity of our compositional specifications. And I think that's all. Bye now. Thank you.